Every second an autonomous vehicle is on the road, it generates gigabytes of data. LiDAR arrays map the street in 3D, radar tracks surrounding objects, and vehicle-to-everything sensors pull in traffic light and pedestrian positions. Traditionally, heavy computing like this happens in the cloud. The car bundles its sensor data and fires it off to a massive centralized server farm that could be hundreds of miles away to crunch the numbers. This split screen tracks the physical reality of that trip. Even at the speed of light, a round trip to a distant server takes around 100 milliseconds. If a car is driving 60 miles per hour, it travels nearly 10 feet. 10 feet is a blind spot. A pedestrian steps off the curb, a truck slams on its brakes. That lag makes a distant cloud server completely unviable for making split-second driving decisions. For self-driving cars, the physical distance to processing power dictates their ability to react. The architectural fix for this distance is mobile edge computing, or MEC. Instead of sending data to a distant warehouse, network engineers install smaller, localized servers directly onto cell towers, streetlights, and traffic signals. This brings the processing power right to the curb. The data only has to travel a few dozen feet, slashing the transmission time from hundreds of milliseconds down to the single digits. But solving distance creates a new constraint. The centralized cloud has virtually infinite processing power. These local edge nodes do not. They are small boxes with strictly limited CPU capacity. This topographical model shows 50 automated cars approaching a busy intersection at rush hour. If every vehicle dumps its heavy collision avoidance processing onto one local streetlight server simultaneously, that node will choke. It drops connections right when they are most critical. Pushing hardware closer to the street is useless if the system cannot manage the traffic influx. To prevent the edge from collapsing, the network relies on a strict internal triage process. The first step happens inside the car itself, a constant calculation known as task offloading. The car's onboard computer has to make a continuous microsecond by microsecond choice. It can process data locally, which burns through its own battery and relies on slower chips, or it can offload the math to the edge server, which saves power but requires transmission time. This logic tree shows how the system handles the load through dependency-aware offloading. It looks at the massive pile of mathematical tasks and maps out which equations have to be solved before others can even start. You can't calculate an evasion trajectory until you've successfully detected the object in the road. The car holds on to the prerequisite tasks locally to ensure immediate safety and beams the heavy, secondary logic up to the edge. The vehicle evaluates its physical environment and completely reorganizes its own computational structure every few milliseconds to keep up. Meanwhile, up on the streetlight, the edge server is fielding thousands of these offloaded requests from every car in a 3-block radius. The server applies the second layer of triage, resource allocation. It runs algorithms to slice up its finite bandwidth and computing blocks among the competing vehicles. To do this effectively, the server operates on one rigid rule. In a vehicular network, data is never treated equally. Look at this resource allocation gauge. If the server receives a critical brake deployment calculation from one car and a heavy 4K map update from another, it instantly compresses the infotainment data. It reallocates all of its computing power to the brake algorithm. It is a ruthless hierarchy. The system intentionally drops digital convenience to enforce absolute priority for human safety. But there is still one major complication. The computers are moving at highway speeds. This creates the handoff problem. A vehicle might offload a heavy chunk of data to an edge server on one street corner, but drive completely out of that server's range before the math is finished. The network uses deep reinforcement learning models to solve this. These AI systems study driver behavior and traffic patterns to predict exactly where a vehicle is heading, migrating necessary data to the next edge server along the route before the car arrives. This 3D network map shows what happens if a car drives into a physical dead zone between two ground servers. The network adapts vertically, pulling in overhead drones or low Earth orbit satellites to act as temporary computing nodes, keeping the data flowing uninterrupted. The network tracks the physical location of every car, calculates where they are going, and warps its own architecture to meet them there. Zoom out to the scale of an entire city, and you see an invisible web covering the streets. Every millisecond, there is a continuous, high-speed negotiation happening in the air. Vehicles, streetlights, drones, and satellites are rapidly bartering over energy, bandwidth, and processing power. The modern automobile is no longer a self-contained mechanical object. It doesn't rely entirely on its own engine or its own onboard computers. A connected vehicle is just one roaming node in a massive floating supercomputer. Building self-driving cars requires solving a much larger equation, conquering the math that governs the edge.